This is a quick review of simplification of radicals. So to start out, we're going to do one that's just very straightforward, square root 36. So you know that is, we can break that down into 6 times 6. And we use 6 times 6 because it's a perfect square. So we know square root of 36 is 6. It gets a little more challenging when we get to one like square root of 80. So I'm going to show you two ways to do one that is irrational. 80 is not a perfect square, so I know that this is an irrational number. The way that you're probably used to doing it is to pull out the primes. Well, the way I usually pull out primes is using the birthday cake method, where I set it up like division. If it's even, I always divide by 2 because I know eventually I'm going to have to anyway. 2 is the smallest prime. I'm just going to work this out, and this is just pulling out primes. And the reason I call it pulling out primes is that notice all of the numbers I divided by are prime numbers, and I divide till I get to 1 on top. That's my little birthday cake candle. So the square root of 80, I can break it down into 2 times 2 times 2 times 2 times 5. Okay, so I'm looking for perfect squares. 2 times 2 is 4, that's a perfect square. 2 times 2 is 2, that's another perfect square. So I'm going to take a 2 out, because square root of 4 is 2, square root of 4 is 2. So I have 2 times 2 on the outside, and I'm left with my square root of 5 on the inside. So I end up with 4 square root 5. So that's probably the way that you've been taught. I'm going to teach you another way to do this that I'm going to call a little shortcut, and that is instead of pulling out primes as we did here, we're going to pull out perfect squares. So think about the numbers that you know to be perfect squares. 4, because 2 times 2 is 4, 3 squared is 9, 4 squared is 16, 5 squared 25, 6 squared 36, 7 squared 49, and so on. So if you just have, the first few of these memorized, you should be in good shape. And this is stuff that you did long ago. Okay, so I'm going to look at this square root of 80 again, and I'm going to solve it using this method. Well, I know that I only have to think about the perfect squares that are less than half or less than. So half of 80 is 40, so I only have to look at these perfect squares. And I'm trying to pick out the largest one. Actually, 36 times, will 36 divide in? No. So 25 won't, 16 will 5 times. So I know that the square root of 80 can be rewritten as 16 times 5. I know the square root of 16 is 4, so this is my answer. Okay, and you can see this is a lot less math to do than this. So pulling out squares, perfect squares, instead of primes becomes a lot quicker solution. So let's do another one like that. So if I had square root of 54, so my perfect squares again, here are my perfect squares. I'm going to think, okay, what's less than half is 27. 25 will not divide into 54. 16 won't, 9 will. So I'm going to write it as 9 times 6 is 54. Square root of 9 is 3. Square root of 6. Okay, so I think that is a much easier way, is pulling out perfect squares instead of using the primes. Now, if you have one that you can't think of a perfect square right away, then that's a great go-to method. So the next thing we want to review is when you have an irrational number like square root 11 in a denominator. So to rationalize that, we're going to multiply by that radical itself. Square root 11 times square root 11 is square root 121, which is just 11. Okay, another example that requires a little bit extra step would be this one. So one way that we could do it is just to do the square root 12, just like we did before. That gives us a 12 on the bottom and 6 square root 12. Now notice here we can reduce, so we end up with square root 12 over 2. Now the square root of 12 still needs to be simplified. So I'm going to do that kind of over here. The square root of 12, if I use my method of pulling out squares, it'd be 4 times 3, so it's 2 square root 3. So I can rewrite the square root of 12 as 2 square root 3. And I'm left with square root 3. Okay, now another topic that we want to review very quickly is the Pythagorean theorem. So remember, the Pythagorean theorem is a theorem that allows us to find the sides of right triangles if we know two sides. So these are my legs. So the leg, the side that's opposite the right angle is always the hypotenuse, and it's also the longest side in the right triangle. So if I had a problem, let's say I knew this was 4, this is 5, and I want to find my third side. So this equation, or the formula, is a squared plus b squared equals c squared, where a and b are the legs. Now, it doesn't matter which one is which because you're adding them, and adding can be done in any order. So I'm going to have 4 squared plus 5 squared equals x squared. So that gives me 16 plus 25 equals x squared. That's 41. Now we're not finished. We have to take the square root of both sides. So in this case, x is square root 41. You can also be missing the hypotenuse, so let's look at that. If I knew this was 12, and let's say this is 3, this is my missing side. Setting it up, so the square of my legs is equal to the square of my hypotenuse. So 3 squared plus x squared equals 12 squared. So 9 plus x squared equals 144. I'm going to subtract 9 from both sides and get 135. Now I still have to take the square root. I'm going to use pulling out perfect squares. So if I write down my perfect squares over here, oops, 49, I'm thinking, so I know that it would be one of these. I know 9 would go into it, so I'm just going to go with 9 and see what happens. So square root of 9 times 15. Is that right? Yeah. So that gives me 3 square root 15 is x. Okay, so now you're going to do a little bit of practice. So choose which one of these topics you need the most help with and start there. So if it's simplification of radicals, rationalizing the denominator, as in this problem, or using the Pythagorean theorem. All of these are going to be necessary skills as we move forward. See you in class.